to be the one talking. I want to talk. I want to talk. I can talk a lot. I can talk. Okay, so the solar day is almost exactly 24 hours. That's what we based it on, yes? We took the time it took to rotate, divided it into 24, right? But a sidereal day, the actual period of rotation is 23 hours, 56 minutes, 4 seconds. Let me show you why. Because as I rotate in space, aren't I also revolving around Joel? Aren't I? Aren't I doing this? Yes? Now I'm basically going to tax the limit. I'm getting kind of choked up about it. The limit of my coordination. The limit of my coordination is that I'm going to try to spin while walking in a circle. Okay? I've practiced this. I really have practiced this, honest to God. Okay? So right now it is high noon. The sun is directly overhead, yes? Joel's like, yes, you could have picked someone else. Okay, but I picked you. Live with it. All right, here we go. All right, so now it is noon on this day, and then 24 hours is noon the next day, right? Joel is directly overhead, or the sun is, right? There it is, right? Okay, so there it is. Okay, so now watch. I have completed one rotation with respect to the stars, yes? My angle of orientation is exactly the same as it was, right? But she's not directly overhead. This is 23 hours, 56 minutes, 4 seconds, a sidereal day. 24 hours, yes? Comes after. Because we're rotating, by the way, from that you can deduce the direction that the Earth revolves around the sun relative to its rotation rate, right? Because anyway, I don't want to go into it, but that's what it is, right? So our period for this thing, for this problem, the period we know is 23 hours, 56 minutes, 4 seconds. Turn that into just seconds. How many seconds is that? Do that right now. Take your calculator. Go 23 times 3600 plus 56 times 60 plus 4.
You know the answer already. Why don't you just tell us?
Just convert. How many seconds in an hour? 3600, right? How many seconds in a minute?
That many.
616 times 10 to the 4.
Is it 86,164? Yeah. Plus or minus maybe a leap second every now and then, a fraction of a second, right? Now, do you want to know the ultimate geeky thing? There are astronomers that have sidereal watches. There is a sidereal time. Now, put this in your pipe and smoke it. Okay? With regular time that the rest of us use, with solar time, every night as you look out, if I go out at midnight and look south, all of the stars every night actually move a little bit toward the west, just like the setting sun. Okay? And a different thing, a star formation that was directly overhead is now a little bit to the right. The next night, and the next night is a little farther to the right, and a different thing is overhead. Different things are overhead at midnight every night, aren't they? But if you had a sidereal watch, the same exact constellation would be overhead at whatever particular time. You could go, oh, it's Virgo o'clock or something like that, right? Yeah? Yeah? Isn't that wild? Now, it might be that it's full daylight and you wouldn't be able to see whatever it is, okay? But it's still there. It's just behind the sun or something like that, right? And you can't see it. But that's, so that's when they when they're reserving time on telescopes, right? You've got to know what's overhead, what's viewable, and that's what a sidereal clock is good for, right? Just corresponds exactly to sky coordinates. Okay, so enough of this. Let's solve the physics. I'm going to use mass of the satellite times 4 pi squared r over t squared. Why am I going to do that? Because I know the period, right? That's going to be g, mass of the central body, mass of the satellite, over r squared.
Well, you can cancel out the mass already.
Yeah, the satellite mass, you just cancel that baby. In fact, you could just start without it. Because we're never going to solve, I'm not going to go into problems where we've got to find the center of mass and figure out the orbit about that. They're not hard, but we're not going to go there. Now, what you want is r on the top and alone. R on the top and alone. So what can I do? Can I slide the r up there? R to the third, and I've got a 1 down here now, right? And can I slide that guy up there? T squared. Don't you love it when people do algebra that way? Can't I take the 4 pi squared and put it down here? And now I'm set, right? I've got r on the top and alone. Do you do math that way? Hopefully you can be a little faster than like cross multiply and then divide. Okay? No, you don't have to show it to me. You can just go. I'm hoping you can just look at that and just by inspection go, okay, r to the cube is that, right? And then what do we have to do now?
Oh, you have to get the plug in all the
We got to do the cube root, right? R is equal to the cube root of g mc t squared over 4 pi squared. Okay? I get kind of emotional when I do that, right? Do you guys know where cube root is? I always cheat, by the way. Privately, I just raise things to the 1/3 power, but you got to put 1/3 in parentheses. It is math 4. Go math button, and then hit 4, or just go down to it. And to type this into your calculator, you're going to go cube root, left parenthesis. Okay? The numerator, you can just lay that thing out there. So 6.67 e minus 11 times 5.97 e 24 times 86164. Don't forget to square it. But now we've got to pause a little bit. We've got a denominator with 2 factors. So we've got to go parenthesis 4. I know you don't have to say times pi squared. I just don't like assuming that a TI calculator will do something predictable. After I tried to square -2 the other day. It's -4. Try typing exactly that into your calculator. Do you see why we've got to have these parentheses here? Because otherwise it divides by 4 and then multiplies by pi squared. And pi squared is this devilish thing that's close to 10. Square pi one time. Pi is really close to the square root of 10. So if you leave out pi squared, or if instead of dividing by pi squared you multiply by it, you're suddenly off by a factor of 100. And we think it's a factor of 100. And then what is the answer with scientific notation, just for fun? Square root. By the way, the fundamental constant of gravity is built into my TI-86. This is actually the calculator designed for physics. The scientific notation button is a first function. I don't have to always go second or whatever. But it does other things differently, so I don't necessarily recommend that you go out and buy one.
What else does it do?
Well, the graphs are slightly different. The matrices, you do them differently.
That's weird.
I like the way it does them better, but it'll be different and you might not like that.
That's weird. I divided by pi squared, the number went up.
That's because you didn't put parentheses around it, I'm thinking. Oh, whoops. Second entry. I just did the square root. By the way, square root's wrong. Okay. Where's my math button? Oh, there it is. Okay, I'm a failure here. Hold on. Okay, so just for fun, I know you might not think it's fun, but I think it's fun. Just for fun, take the number that's on your calculator and just divide it by, go divide it by 6.38 E6. That's the radius of Earth. Just divide it by the radius of Earth. Do you get like 6.6 roughly? Yeah, it's like 6.6 Earth radii. Radius of the Earth. This is not something you commonly do. It's just something that's going to help us visualize exactly where this thing is. So here's the Earth. Point your eyes up here. Here's the Earth. Here is one Earth radius is about this much, yes? Now, these satellite orbits are right off the equator. That's the only way that they can actually stay in the same spot in the sky, right? Is that they're right here off the equator, moving around like this. It is 6.6 from the center. So right now I am actually 2 Earth radii from the center, aren't I?